Hey guys, welcome back to physics. Today we're going to be talking about acceleration. It's the first of 2 days about acceleration. And in these notes, we're simply going to define what it is and look at the basic equation for it. So the definition is that acceleration is the rate of change of velocity, which is how velocity changes over time. And acceleration is a vector, just like velocity, meaning it has a magnitude or a size and also a direction. And since it has both, either one can change and it counts as acceleration. So we'll first think about magnitude changing. Magnitude means size, okay? So if the magnitude of velocity changes, or the size of the velocity, the numerical value, then you could be going from 10 meters per second to 5 meters per second. And when you're decreasing the magnitude, we call that slowing down. And typically in the real world, we call that deceleration, but it technically does count as acceleration, since acceleration just means your velocity is changing. It doesn't indicate if it's getting bigger or smaller. So slowing down is one option. The other way to change the magnitude is to increase it, say from 10 meters per second to 15 meters per second. When you get a larger velocity, that is speeding up. Now our third option, most people don't usually consider, and that's the other part of the vector, that is the direction. So you can change the direction of motion of an object, and that also counts as acceleration. So for our third spot here, we can put changing direction. That's like turning on a curve or something like that, where you're not going in a straight line anymore. You are changing your direction. So those are the three options for acceleration. For the math, we're going to only be dealing with these first two, because changing direction does all sorts of crazy things, and that's more like circular motion, which we're not going to go into just yet. But we're going to be focusing on those top two, which just change the magnitude. So let's get on to the equation. The equation for velocity, or not velocity, sorry. The equation for acceleration looks really similar to the velocity one. It is changing velocity, okay? So that's a delta for the change and v for velocity. We're changing velocity. We're seeing how long it takes, so that's the delta t again. And that equals our a for acceleration. So we've got delta v is change in v, change in velocity. Delta t is change in time. A is acceleration. Now, when we were doing the delta x for velocity, usually things are given as a distance. They don't tell you where it started and where it ended. But velocity is given differently, usually in questions. So instead of writing delta v in the equation, most of the time we're going to be looking at the final and initial velocities. So final means the velocity at the end, and initial means the velocity at the beginning. So in order to figure out how much it changes from the beginning to the end, you always do the last velocity, or the final velocity, minus initial. So delta v can be written as final velocity minus initial velocity. And what that does to our acceleration equation is change it up a little bit. Instead of writing the delta v, we can write it as vf minus vi, that's the delta v, divided by delta t equals a. So that's going to be the main equation that we use. Vf minus vi, which is the final velocity minus the initial velocity, divided by delta t, equals a for acceleration. So let's scoot on down here and do a practice problem with that. Practice problem 1 says, what is the acceleration of a car if it goes from rest to 27 meters per second in 2.8 seconds? Assume the car is moving in the positive direction. Now, on these questions, instead of doing an image for your eye, we're going to start doing position time graphs, which we learned last class. So a position time graph looks like this, where this is time and this is position. And we're just going to draw a graph that matches this motion. So this car goes from rest to 27 meters per second. Okay, If you're starting at rest, that means you're starting off at 0 meters per second. So you're starting off still and you're speeding up. Now we know from last class that a graph that is starting from rest or starting slow looks kind of horizontal or flat, and then as it speeds up, it curves. Now our question here does say assume it's moving in the positive direction, so this graph works out because it's moving up in the positive direction. If you did this graph, it's still speeding up, but it's not moving positive. So you got to have the one that's going up in the positive direction. And then we'll move over to the givens and the unknown. Now the givens here, there's two numbers that we can go ahead and immediately write down. One is that 27 meters per second, and then the other one is 2.8 seconds. Now let's go ahead and label those. So it says it goes from rest, which is where it starts. So it starts at rest, to 27 meters per second. From always indicates the initial, to always indicates the final. So if it says from, that's the initial, to is the final. So 27 meters per second is going to be our final velocity. And then the 2.8 seconds indicates time, so that's our delta t. Now we need one more given, and it's kind of hidden in the question here. This word rest, okay? From rest means it is starting off, from means starting off, and rest means still. If you are still, your velocity is 0. So we're going to have 0 meters per second be a given, and that is our velocity at the beginning, initially. So we got 3 givens, and the question wants to know what is the acceleration. So that's our unknown, acceleration. And now we go to the equation. The equation is VF minus VI over delta t equals acceleration. I'll go plug some stuff in. VF is 27, VI is 0, delta t is 2.8, and acceleration is what we're looking for. This one's nice and easy because there is no algebra. You just have to do 27 minus 0 divided by 2.8. And I guess that mine here looks like it's equals 9. That's not an equals 9, that's an equals a. Let me go ahead and type that in on a calculator really quick. 27 divided by 2.8 is an acceleration of 9.6, and the unit for acceleration, meters per second squared. So we get that. And it is positive, which means we're accelerating in the positive direction, okay? Nowadays, since we've learned about positives and negatives, we don't have to start putting right or left or anything like that for vectors. We just now rely on the positive or the negative. So we can also use this equation that we already know. It's VF minus VI over delta t equals acceleration. We can solve that for all of the other variables. That way we can find final velocity, initial velocity, delta t, or whatever. So we're going to go ahead and solve that for each of those variables here. And it's going to take us just a minute. I'll go ahead and write my equation down. And this one we're going to solve for VF. Right now, I'm going to highlight VF so we know where it is. Right now, VF is right here. And it's got some other stuff with it that we don't want. It's got a VI that's subtracted and a delta t that's divided. So, first things first, we got to get rid of that division there. Okay, to get rid of the divided by delta t, we're going to multiply by delta t on both sides. Okay, so these ones cancel out and go away. And you end up with just VF minus VI equals A times delta t. Beautiful, except for our VF over here still has the VI that we need to get rid of. It's being subtracted. The opposite of subtraction is addition. So we will add it to one side. What you do to one side, you got to do to the other. So you get velocity final equals VI plus A delta t. Okay, and that would be your final formula for VF. Now VI is pretty similar. We start off with the same equation, VF minus VI over delta t equals A. But now we're going to be solving for VI. Now VI is over there with VF and delta t. We don't want those anymore. So first things first, we have to get rid of the delta t. It's being divided, so we multiply on both sides. Crosses out there, cancels out. Well, now we have VF minus VI equals A times delta t. Now you got two options here. You can either move the VF over and divide by -1, or you can move the VI over and then the A delta t over. I'm going to do it first by subtracting VF. Okay, so VF gets subtracted, and you get negative VI equals A times delta t minus VF, and then you can divide everything by -1, which gets you VI equals negative A times delta t plus VF. Or you could switch those around and do VF minus A delta t. Up to you. But that's our equation for VI. And then for delta t, we get to do some fun algebra. We've got VF minus VI over delta t equals A. Now this time we're solving for delta t. It is in the bottom. And we should know by now you can't solve for something that's in the bottom immediately. You got to cross multiply it up, okay? Or you can multiply by it on both sides, which is essentially the same algebraic operation. But you multiply by delta t on both sides, these ones cross out, and you end up with A times delta t over there on the right. So you get VF minus VI equals A times delta t. To solve for delta t over here, the acceleration needs to go away. Right now they're being multiplied. So we'll divide on both sides, those ones cross out, and you get delta t equals VF minus VI over A. So that's how you're going to algebraically solve for all of those different things. You need to be able to do each of those on your own when it comes to word problem time. Now we're going to scoot on down here to another word problem to use those algebraic skills. This question says, what is the final velocity of a car if it starts at positive 6 meters per second and accelerates at negative 2 meters per second squared for 2 seconds? What about 3 seconds? What about 10 seconds? Okay, so really we have 3 different problems here because we're looking at 3 different times. But we're starting off with a position time graph. Okay, and the position time graph here is kind of hard to figure out right at first. We're starting at 6 meters per second, so we're starting off going positive. We know that much. But then we're accelerating at negative 2 meters per second squared. What does that mean? Well, let's actually do the math first and draw the graph last. That way we can figure it out. Starting with the givens, okay, just for the first question, we know it's going to start at positive 6 meters per second. So when it starts, that's the VI, 6 meters per second. We know it accelerates at negative 2 meters per second squared for 2 seconds. Okay, so that's a delta t of 2. That's our first givens. Okay, we're going to have 2 more questions later. And then our question asks, what is the final velocity? That's VF. Okay, so our equation is acceleration equals VF minus VI over delta t. Or if you'd rather use the one that's already solved for VF up there from earlier, go for it. We're going to plug things in. Acceleration is negative 2, and that equals VF, which we don't know, minus VI, which is 6, divided by delta t, which is 2. So our algebra steps say that we should multiply by 2 to begin with, which gets us negative 4 equals VF minus, that's a plus, minus 6. And then to solve that, you got to add 6 to both sides. Negative 4 plus 6 is positive 2. So your VF equals 2 meters per second, and that's after 2 seconds. Okay? So after 2 seconds, we end up being 2 meters per second. So let's look at that on our graph. We started off at 6 meters per second, so our slope should be pretty steep. But then we slowed down to 2. Okay, so we're going to curve off to be a little bit slower. Now if we look at 3 seconds, let's figure out what happens. We do acceleration equals VF minus VI over delta t But this time we're going to make our delta t 3 seconds, okay, instead of 2. So we substitute everything in. Negative 2 equals VF, which we don't know, minus 6, this time divided by 3. So we're going to solve this the same way. Multiply by 3 on each side. 3 times negative 2 is negative 6 equals VF minus 6. If you add 6 to both sides on that one, you get 0 equals VF. So at time equals 3 seconds, your final velocity is 0, which means you're flat. Okay, you've stopped. Right at 3 seconds, you're stopped. Then we're going to do 10 seconds. See what's happening at 10 seconds. So we'll switch this delta t to 10. Same steps. Acceleration equals VF minus VI over delta t. Now it's negative 2 equals VF minus 6 over 10. So this time we're multiplying by 10 on both sides. Those cancel out. You get negative 20 equals VF minus 6. Add 6 to both sides. And this is now negative 14 equals your VF. Okay, that's going pretty quick in the negative direction. So our graph is now going to need to have negative slope. And it is going to be getting faster and faster and faster. So your graph now looks like that. Okay, we're accelerating in the negative direction. There you go. We got one last question to look at. Oh, all of my writing did not move with that. Give me a second. We're going to get rid of it. Okay. This last question says, what are the conditions for speeding up versus slowing down? Note that negative acceleration does not always mean slowing down. Positive acceleration does not always mean speeding up. So let's think about this in kind of picture form. I'm going to make, this is just showing you directions. Positive is to the right, negative is to the left. Okay, so imagine that I have this runner here running to the right, okay? That means his velocity is in the positive direction, okay? If I push him from behind, okay, if I push him like this, that's going to make him accelerate, okay? When you push on something, it makes it accelerate. So if I push with him, my push or my acceleration is in the positive direction. If I'm pushing my runner from behind, what's he going to do? Well, he's going to speed up. And that makes sense. But if I push him from the front and make my acceleration negative, okay, oh, I put -1. I just meant negative. Let me erase that really quick. If I make my acceleration negative, going towards the negative direction, so my rudder's running positive, I'm pushing him negative, he's going to slow down. All that makes sense. But let's flip it and see what happens. Okay, it's going to take me a second to make my runner flip here. All right, there he goes. So this time, I'm going to make my runner go in the negative direction. The velocity is negative. Oh, I did -1 again. There's negative. Okay, so velocity is negative. Now, if I push my runner in the positive direction, my acceleration is positive. What is going to happen to the runner? If we think positive acceleration means speeding up, then this makes no sense, okay? Because the runner is running against the push. Push is against him. If there's a push against the runner is going to slow down, even though my acceleration is positive. But this time, if I push him from behind, which makes my acceleration in the negative direction, then he's going to speed up, even though the acceleration is negative. So the conditions here are that if your velocity and your acceleration are in the same direction, so they're either both negative or they're both positive, then you speed up. But if they're in opposite directions, one is positive and one is negative, you end up slowing down. So when you're considering them, the velocity and the acceleration, if they're both the same, both positive or both negative, you're speeding up. If they're opposite, one's positive, one's negative, you're slowing down. All right, that's all I've got for you on velocity today. You do have a practice. It's 8 questions long. It's in Google Classroom. All of the answers are there so you can check yourself as you go. And as always, feel free to email me if you need anything, got any questions, let me know.